All right, stop for a second.
Before you blink, before your coffee cools, before gravity quietly holds you to your chair without asking permission, do you actually know what gravity is, or are you just used to it? Because I'm Richard Feynman, a physics genius if the newspapers insist, a Nobel Prize winner if you like titles, and I'm telling you right now, gravity is the one thing in physics we pretend to understand and we don't. That SIP's not a teaser. That SIP's a confession. People think gravity's obvious. Apples fall, planets orbit. You stick to the Earth instead of floating off like a balloon. Very comforting, very neat. But comfort is the enemy of curiosity, and curiosity is the only reason physics exists at all. In this video, I'm going to do something most textbooks never dare to do. I'm not going to give you equations first. I'm not going to hypnotize you with symbols. I'm going to tell you why gravity is still a mystery, why every confident explanation you've heard is quietly incomplete, and why that should make you excited, not disappointed. And if you watch until the end, you'll understand something most people, including many physicists, never fully grasp, that not understanding gravity is not a failure of science, it's the engine of it. Here's a lesser-known fact about me. During the Manhattan Project, while the world was racing to build the most destructive device in history, I spent my free time cracking safes for fun. Not because I needed to, but because I wanted to know how they work. That itch, that refusal to accept surfaces, is the same itch that makes gravity so infuriating and so beautiful. You see, people often say gravity is a force. They say it with the same confidence they say the sky is blue. But confidence is cheap. Understanding is expensive. We can calculate gravity with astonishing precision. We can predict eclipses centuries in advance. We can land probes on moving rocks millions of miles away. Newton gave us the math. Einstein refined the picture. But here's the dirty little secret. Calculation is not explanation. That's one of the most misunderstood ideas in physics. When you watch this video, you'll learn the difference between knowing how something behaves and knowing what it really is. You'll see why physics answers questions in layers, and why gravity stubbornly refuses to peel cleanly. I once told an interviewer that nobody understands quantum mechanics. People laughed. They thought I was joking. I wasn't. And gravity is even worse. Quantum mechanics, strange, counterintuitive, almost mischievous, works beautifully for 3 of the 4 fundamental forces. Electromagnetism, we've got it. The strong force, nailed down. The weak force, messy, but obedient.
Gravity? Gravity sits in the corner, arms crossed, refusing to cooperate.
In this video, I'll walk you through why gravity doesn't behave like the other forces, why it resists being quantized, and why that failure is one of the deepest clues we have about the universe. This isn't just history, it's an open wound in modern physics. Another fact you may not know, I was deeply suspicious of authority. Titles didn't impress me. Consensus didn't comfort me. I believe that the moment science stops admitting confusion, it stops being science. And gravity is the perfect example.
Textbooks often tell you that gravity is a curvature of space-time. That's a lovely sentence. It sounds profound. But if you think that sentence ends the conversation, you've missed the point entirely. It just opens a deeper one.
In the next few minutes, you'll hear me challenge common sense physics. Not to confuse you, but to sharpen you. I'll show you why the idea of gravity as a pull is a mental shortcut, not a truth. Why asking what causes gravity is still a dangerous question in a room full of experts. And here's why you must watch till the end, because near the end of this journey, you'll see why confusion is not something to escape, but something to cultivate. That's not motivational nonsense. It's how real discovery happens. When I won the Nobel Prize, people expected me to act wiser, calmer, more certain. I didn't. I stayed confused on purpose. Confusion means you're still learning. Certainty means you've stopped looking.
This video isn't about giving you comfort. It's about giving you vision.
You'll learn how a physics genius thinks when the answers run out. You'll learn why quantum mechanics and gravity clash like mismatched gears. You'll learn why admitting I don't know is sometimes the most honest and powerful statement a scientist can make. And most importantly, you'll learn how to look at the universe not as a finished book, but as an unfinished draft with footnotes still being written. If that idea excites you, if curiosity still burns a hole in your pocket, then you're exactly where you belong. Welcome to Feynman Flux, a channel for people who don't just want answers, but want better questions. Subscribe, stay curious, and don't trust gravity just because it's always been there. Imagine this. You're sitting on a swing as a kid, pumping your legs, flying back and forth, and you feel that invisible pull that keeps you tethered to the earth. You think you understand it, right? Gravity, obvious, simple, nothing to worry about. But what if I told you that even a physics genius like me, Richard Feynman, spent his entire life wrestling with the idea that gravity might not be what you think it is? What if I told you the most honest explanations of gravity don't come from complicated equations or high-tech laboratories, but from nothing more than clear, careful thought? That's exactly how I approached physics from the very beginning. As a kid growing up in Far Rockaway, New York, I had a compulsive curiosity. I took apart radios before I knew what radio waves were. I figured out how locks work just to understand them. And I asked questions that annoyed teachers. Why does this work? What is really happening? That same curiosity drove me into the mysteries of gravity. I didn't start with textbooks. I started with thought experiments, mental exercises, imagining worlds, situations, and possibilities, and asking questions no one else dared.
I love thought experiments because they strip physics down to its bare bones. No equations, no instruments, just honesty and logic. You can explore the universe with nothing more than a pencil, a scrap of paper, and a restless mind. That's the power of mental experimentation. And when it comes to gravity, it's the only way to glimpse its true strangeness. People often try to explain gravity with metaphors, a stretched sheet of fabric, an invisible hand pulling objects, but I avoided those. I wanted clarity, not comfort. If a concept couldn't be explained cleanly, I said so. That kind of honesty made me famous, not just for winning the Nobel Prize in physics, but for showing the world that it's okay not to understand everything immediately. Let me take you into one of my favorite thought experiments on gravity. Imagine floating in space, far from planets, stars, or anything else. There's no floor, no ceiling, no up, no down. Now imagine a ball suddenly appears in your hand. What will it do? At first you might say, it falls. But falls where? There is no down here. This forces you to confront a deeper question. What is gravity really? We tend to think of it as a force pulling objects together. But in the emptiness of space, that metaphor starts to crumble. And that's exactly the point. Physics isn't about comforting metaphors. It's about finding the simplest, clearest truth underneath the illusion. I remember as a child, I once dropped a pebble off the roof of our apartment building and timed how long it took to hit the pavement. I wasn't interested in winning a bet with my friends. I was fascinated by the behavior itself. I wanted to predict it, understand it, and yet even then, the simplest action, falling, was more mysterious than anyone imagined. That same curiosity stayed with me all my life, and it's why my approach to gravity was always rooted in imagination first, numbers second. Einstein gave us the notion of gravity as curved space. Beautiful, elegant, mathematically impeccable. But here's the thing, even to a physicist, it feels weird. Imagine being inside a trampoline stretching and bending under your weight, with balls rolling along the curves. That's the common metaphor, yes, but the reality is stranger. Space itself bends. Time itself bends. And yet, even knowing the equations, even understanding the theory, your brain rebels. That's why thought experiments are so crucial. They let you feel the strangeness without being paralyzed by symbols. They make physics human. I've always insisted that physics should feel human. That's why I avoided hiding behind equations when I taught. Numbers are essential, yes, but they can never replace curiosity. When I taught at Caltech, I often started lectures with little puzzles or stories, just to get students thinking. One day I would ask them to imagine being inside a freely falling elevator. Another day to picture a planet orbiting a star without saying a word about Newton's laws. And students learned faster, not because they were memorizing, but because they were experiencing the logic. That's how I approached gravity. Experience it in your mind before you try to formalize it on paper. Another little known fact, I had a notebook as a boy where I drew all sorts of imagined machines and contraptions. Some were ridiculous, some impossible, but every single one started with a question, how does it work? Why does it move like that? Gravity fascinated me because it was everywhere, yet completely invisible. Unlike electricity, which hums and sparks and can be felt, gravity quietly shapes the universe, silently bending paths of planets and pebbles alike. That silence makes it harder to grasp, but also more poetic. My thought experiments tried to listen to that silence.
Here's one that always sticks in my memory. Imagine standing on a tiny planet small enough that you could jump and circle to the other side. What does up even mean there? The idea of falling starts to lose its obviousness. Suddenly, gravity is not just a pull, it's a relationship between masses, distances, and motion. And the closer you look, the less comforting metaphors become. That's the lesson I wanted everyone to feel. If something about physics feels weird, that's the point. Curiosity thrives in the discomfort of not understanding. Confidence comes later. First comes the feeling of wonder, the itch of confusion. I never liked taking shortcuts in understanding. When I read popular books or listened to casual explanations of gravity, I would cringe at the simplifications. The apple falls because Earth pulls it. Fine for dinner conversation, useless for thought. True curiosity demands more. What is being pulled? What is the meaning of force here? Can we imagine a universe without the concept of pull and still make sense of motion? These are the questions I love, and they're the questions that thought experiments can answer far more deeply than any formula. And I'll tell you another secret. I used to sketch imaginary universes just to see what would happen. Worlds with two suns, planets orbiting strange stars, objects moving in ways that seemed impossible. And every time gravity revealed itself as simultaneously simple and baffling. Simple because its effects are predictable, consistent, and obeying rules we can calculate. Baffling because the underlying mechanism, the why, remains hidden. That tension is the heart of physics. That tension is curiosity itself. Even today, when students or colleagues ask me about gravity, I insist, don't just recite Newton or Einstein. Imagine, think, place yourself in situations where gravity behaves differently or unexpectedly. Let your mind feel the force or the absence of it. That is the real education. Numbers will follow, equations will follow, but without the thought experiment, without the mental stretching and bending, you've never really met gravity.
I want you to picture that right now. Floating in a box, far from planets, let go of all your assumptions. Let go of down and pull. Think about the motion of objects around you, the curves of space-time, the silent, invisible rules shaping everything. That's where the real story of gravity begins, not in classrooms, not in textbooks, but in the raw human act of thinking, clearly and honestly.
And that's the secret that kept me excited about physics my entire life. Even with a Nobel Prize, even with fame, even with the most complex quantum mechanics and the most precise measurements, the most thrilling moments were always the ones when I said, I don't fully understand this yet, but maybe I can imagine it.
Curiosity before confidence. That's the lesson I hope you feel as we explore these thought experiments together.
Gravity. It works every time. Drop an apple. It falls. The planet's orbit. You sit down and you stay put. Perfectly reliable. Predictable. Beautiful. Yet, here's the thing. No one fully understands why. Not Newton. Not Einstein. Not even me. Richard Feynman. And that, my friends, is exactly what makes it fascinating. Not frustrating. Fascinating.
You see, I've always believed that physics is a description, not reality itself. The equations, the models, the diagrams, they tell you how things behave. They don't tell you what things are. Newton's law of gravitation, wonderful, elegant, predicts motion with precision. But does it explain what gravity truly is? No, that's a mistake people make. Confusing the map with the territory. The math is the math. Reality is something else entirely. And separating those two, that's where real understanding and curiosity begin. Even as a kid, I had a restless mind. I wanted to know what made the world tick. I took radios apart, locks apart, anything I could get my hands on. The Manhattan Project gave me bigger toys, splitting atoms, calculating critical masses, but the itch never left. And gravity is a bigger puzzle than any bomb or particle, because it's everywhere, always. It's simple, yet profoundly mysterious. Classical physics, Newton, gives us rules, predictable motion, elegant orbits, falling objects. But the essence, the why, it stops there. Newton gave us the how, not the what. Then came Einstein, curved space-time. Geometry is gravity. Brilliant, but still weird. Counterintuitive. Even today, physicists feel that strangeness. That's where thought experiments come in. Imagine being inside a freely falling elevator. Everything floats. Objects move as if there is no gravity. That's Einstein's universe in action. And yet it still doesn't answer the ultimate question. Why does gravity exist at all? Then we get to quantum mechanics. That's where things get even messier. On the scale of atoms and particles, gravity fades into insignificance. Electrons dance to quantum rules. Photons zip along. Quantum electrodynamics dominates. And gravity? Almost invisible. This wasn't a frustration to me. It was a warning sign. Physics is incomplete. Our understanding is patchwork, and that patchwork is thrilling. It's a sign that there's more to discover. I spent a lifetime working with quantum electrodynamics. Feynman diagrams sum up interactions in neat visual ways. Nobel Prize for it, yes? But even while calculating the interactions of light and matter with astonishing precision, I knew gravity refuses to play by these rules. That's exciting. That's the signal that the universe is bigger than our current models. The unknown isn't a threat. It's an opportunity. Even on the Manhattan Project, surrounded by engineers, mathematicians, and physicists, all following strict procedures, I found myself asking weird questions. Not just does it work, but why does it work like this? That mindset followed me through life. And gravity is the perfect puzzle for it. It works every time, and yet its underlying nature remains elusive. That tension, the certainty of observation, and the mystery of explanation is intoxicating. I've always trusted curiosity more than authority. Nobel Prize committees, famous physicists, textbooks, they have authority. But curiosity drives progress. That's why I love unanswered questions. They point to where physics is incomplete. They whisper that the universe has more to tell us. And gravity is full of whispers. Imagine trying to fit gravity into quantum theory. Tiny scales, energetic particles, unpredictable probabilities. Gravity refuses. No neat diagram, no tidy calculation, just stubborn behavior. This tells you something profound. Our models are tools, not truths. Equations describe patterns. Reality is richer, stranger, and more subtle. And if you embrace that, the thrill of physics comes alive. Even now, when students or colleagues ask me about gravity, I tell them, don't be afraid to say, I don't know. Don't be afraid to sit with uncertainty. Some of the most exciting discoveries come from admitting gaps in understanding. Feynman diagrams, quantum electrodynamics, they were breakthroughs born from asking deeper questions, from noticing inconsistencies, from trusting curiosity over the comfort of authority. Gravity also reminds us that classical physics has limits. Newtonian mechanics is beautiful, but it's only an approximation. Einstein expanded the map, curved space-time, gravitational time dilation, mind-bending concepts. Yet even Einstein couldn't bring quantum mechanics fully into the mix. That boundary where classical meets quantum is a frontier, and frontiers are where physicists, real physicists, get their energy. I want you to imagine it. Right now, a universe where every law we trust is just a description. A universe where falling apples, orbiting planets, and bending light are all phenomena we can calculate, predict, even manipulate, but whose essence remains a mystery. That's the playground of the mind. That's where thought experiments, imagination, and curiosity matter more than authority or memorized facts. I often say that physics is not about certainty. It's about structured doubt. You calculate, you predict, you test, and yet you always know there's more beneath the surface. Gravity is the perfect example. Every calculation succeeds. Every prediction holds. And still, we are left with wonder. That wonder drives questions, thought experiments, and eventually breakthroughs. Even the strongest minds, Newton, Einstein, Bohr, me, feel this tension, and it's beautiful. Because physics isn't about having all the answers. It's about asking better questions. What is the mechanism of gravity? How does it connect with quantum mechanics? What happens inside a black hole? Each unanswered question is an invitation. Each contradiction is a signal that our understanding is still growing. And that's why I never feared uncertainty. The Manhattan Project taught me the power of applying science to real-world problems, but it also taught me the joy of thinking deeply about impossible puzzles. Nobel Prizes and recognition are fine, but they are fleeting. The lasting excitement comes from wrestling with the unknown, from staring at the stubborn behavior of gravity and saying, interesting, let's see what else we can discover. Even when teaching, I would encourage students to embrace confusion, to sit with the mystery, to ask questions that might seem naive. The best discoveries often start with that simple curiosity. Why? Gravity is the ultimate teacher in this regard. It works every time, it's everywhere, and yet it refuses to be fully explained. That contradiction is the gift of physics. And so when I think about gravity and reality, I see a universe full of patterns waiting to be discovered, equations waiting to be drawn, and questions waiting to be asked. Quantum mechanics, general relativity, Feynman diagrams, quantum electrodynamics, all tools to explore the unknown. but the unknown remains. And that's not a flaw. It's the reason we keep going, the reason physics is alive. Gravity reminds us our descriptions of the universe are provisional, our models imperfect, our understanding always incomplete. And that's exactly how it should be, because incomplete understanding is the spark of curiosity, and curiosity is the engine of all breakthroughs. We calculate, we predict, we diagram, and yet we remain humble in the face of the universe's stubborn mysteries. That was my way of thinking. And if you let yourself see it, it becomes your way too. The unknown is not something to fear. It is something to explore, to imagine, to love. And gravity is the ultimate invitation. You've probably heard me say it. We don't understand gravity, and I know people freeze when I say that. How can a physics genius, a Nobel Prize winner, a man who helped build quantum electrodynamics, admit something so basic escapes him? Gravity works every time. Apples fall, planets orbit, satellites follow paths we calculate to the second. And yet I say it anyway, because there's a distinction most people miss, a distinction between predicting and understanding. Physics is spectacular at predicting outcomes. Drop a ball and it hits the floor exactly when you expect. Launch a rocket and it reaches its target. That's power. That's what equations do. But prediction is not explanation. Knowing how something behaves is different from knowing what it really is. That's the gap gravity exposes. I could teach a student every formula about falling objects, every equation about curved space-time, and still say, I don't understand it. That honesty is uncomfortable, yes, but it's also liberating. It frees you to ask questions that no textbook dares to answer.
Language itself fails us in physics. Words feel solid. You think you're describing reality, but reality doesn't obey the neat constraints of language. I warned about this in quantum mechanics too. You can calculate probabilities of particles appearing, interactions happening, and yet every description sounds almost poetic, almost fictional. Gravity is no different. You can describe it as a force, or as curvature of space-time, or as a field. Each description works, but none is reality. They're tools, not truths. And that's what I meant by not understanding.
Human intuition is another trap. Gravity evolved with us. We've walked on Earth for millions of years, so our senses align with classical experiences. But quantum mechanics, it did not evolve with us. Gravity at tiny scales, inside black holes, or near the edge of the universe, behaves in ways that make intuition meaningless. That's why learning physics often feels uncomfortable. That's why even brilliant minds like mine have to constantly question, imagine, and rethink. Our intuition can guide us, sometimes, but it can also mislead us.
Curiosity is the real engine here. Science is not about certainty. Science is about asking questions that might never be fully answered. And gravity is perfect for that. It works without fail, yet its essence is still a mystery. That tension keeps physics alive. It keeps us exploring. It keeps us imagining. I've spent decades working with equations, Feynman diagrams, quantum electrodynamics, and yet the thrill of asking, what is really happening, never faded. That's the core lesson. Curiosity matters more than the answers.
Gravity still works. Satellites orbit. Apples fall. Predictions hold. But its meaning remains open. And that's okay. That's exactly what makes physics exciting. I wanted students, colleagues, and anyone who would listen to feel comfortable with not knowing, to embrace confusion, to let it drive exploration, because science is unfinished, and that's the point.
If even someone like me, Richard Feynman, stayed curious until the end of his days, then there's no reason you shouldn't either. Let the unknown fuel your imagination. Let questions guide you. Let the beauty of the universe overwhelm your assumptions.
If you enjoyed this exploration of how I thought about gravity, physics, and curiosity, take a moment to like this video, leave a comment sharing what you found most surprising, and subscribe to Feynman Flux. There's a whole universe of ideas waiting for you, more videos where we explore quantum mechanics, the secrets of the cosmos, and the mindset of curiosity-driven science.
Don't stop asking. Don't stop imagining. Stay curious. Explore more. The universe is waiting.